Hi everyone, Ross Satchel from Microchip back again. Welcome to episode 14 in our AVR Bare Metal series. In the previous video, we wrote basic SPI drivers for both host and client devices and sent a byte from the host to the client. The client then sent back the last byte received. In this video and the next, we will build our final project using almost all of the drivers we have created over the past 13 episodes. The final project consists of two AVR-DD Curiosity Nano development boards. One is the host, while the other is the client. Both will first initialize, and then move into the lowest power sleep mode. When the button switch on the host is pressed, it will wake up, take an ADC reading along with a window threshold, then send that data over the SPI bus to the client, and then finally return to sleep and wait for the next button press. When the host's SPI client select line is pulled low by the incoming SPI data, the client device will trigger an interrupt and wake from sleep, receive the incoming SPI data block, convert the SPI data into a human-readable format, and then write that out to the USART. Finally, the client device will return to sleep and wait for the host to send more SPI data. So let's get started. I'm going to use a state machine for each of the host and client devices. I won't go into state machine design and implementation here, as there is already available content. If you want more information on implementing a state machine, take a look at the Microchip University course titled Getting Started with PIC16F1XXX MCUs using MCC and state machines. You can go to the URL shown on screen or click the link in the description below. While this implementation does not use a PIC microcontroller or MCC, the state machine implementation is the same. Let's start with the host device state machine. The states are initialize, switch to high-speed clock, read ADC, send SPI data, switch to low power clock, and sleep. The state machine will sequentially move between the states as shown by the arrows, except for the sleep state. The only way to get out of the sleep state on the host device is for a pin change interrupt from a button press to occur. Now for the client device state machine. The states are initialize, sleep, switch to high-speed clock, receive SPI data, switch to low power clock, and write to USART. The state machine will sequentially move between the states as shown by the arrows, again except for the sleep state. The only way to get out of the sleep state on the client device is for an incoming data transfer from the host to occur. Now let's look at the wiring diagram. Similar to the previous episode, we have an SPI bus on pins PA4, PA5, PA6, PA7 with the signals MOSI, MISO, SCK, and SS respectively. Don't forget to connect ground between the host and client device. We also have an analog sensor that will be powered using I/O pins on pins PC2 and PC3, with the analog output of the sensor on pin PF2. Let's jump to MPLABX. I will start with the host device. First, we need to include the header and source files that we've created during this series. If you're not sure how to add existing header and source files, see episode 9 in this series. The host device will need the main clock control library, USART 0TX library, SPI 0 library, ADC library, ports library, and sleep library. We also need to define the fCPU macro for any delays that we use. The majority of the time in this project, we will use the 32.768 kHz ultra-low power internal oscillator. We also need to add some XC8 libraries as well. We need the interrupt library and delay library. Next, we have another define for the number of SPI bytes to send, and this is set to 2 bytes. There is a comment above the define describing how this is used. Then we have two more defines for the window satisfied and window not satisfied criteria. Let's take a look at the anatomy of an SPI data block that we will be sending. When deciding how to send the ADC result and the window comparison result, I noticed the 12-bit ADC result had 4 bits unused. So instead of sending 3 bytes, where 2 would be the ADC result and 1 would be the window comparison result, I decided to take advantage of the unused bits in the ADC result and used the most significant bit in byte 1 as the window comparison result. Jumping back to MPLABX to the window satisfied and not satisfied defines, that they match the diagram in that we will shift either a 1 or a 0 to the most significant bit of that byte. Then an array to hold both SPI bytes is defined. Next, we have a function called spinlock, which takes an unsigned 16-bit integer parameter called time in milliseconds and has a void return. The purpose of this function is to provide a type of delay function without having to redefine the fCPU macro, which is used for delays. I will talk more in depth on this in the gotchas section of the final episode, episode 15. For now, the important things to know are that it converts milliseconds to microseconds and includes a scaling factor that was determined from 2 factors. Firstly, the NOP or no operation instruction execution time when using the 4 MHz clock is 0.25 microseconds. And secondly, a scaling factor was required to account for the for loop overhead. The scaling value was determined using the data trace of my logic analyzer. Next is the state machine type definition of an enumerator with the states outlined in the host device state machine with the type of app states. Then I created a type definition of type app data, in which we declare a variable called state of type app states. If this is new or confusing to you, take a look at the Microchip University course on state machines I referred to earlier and is linked in the description below. In the main function, we start by creating a variable of the app data type and name it lowercase app data. Now I can use dot notation to set the first state to init. Now for the while one loop. The entire loop is a switch case statement. In the case of the state being init, we first set up a low power clock to run at 32.768 kHz. Let's control-click on the function to go to its definition. We can see the parameters for the function are the clock selection, prescaler enable, prescaler divider, run standby, and clock out. Just as with our main clock control function, we need to perform protected write operations on any register specified as a configuration change protection register. In main clock control A, we write the clock selection bit field and the clock out bit. Main clock control B, we write the prescaler divider pdiv bit field and the prescaler enable bit. The next register is OSC32K control A, which sets the run standby bit. Recall from previous episodes that the run standby bit allows a peripheral to continue running in certain sleep modes. Returning to the main.c file, we call the low power clock control function, select the internal 32.768 kHz oscillator, no prescaler, which means that whatever we put in the pdiv or prescaler divider parameter will be ignored. Then run standby is 0 and clock out is also 0, both to reduce current consumption. Next, we call the port init function. So let's control-click to go to the definition. The AVR-DD Curiosity Nano has 4 ports, A, C, D, and F. The SPI pins are on port A, pins 4, 5, 6, and 7, while the button switch is on pin PF6. However, because we want to minimize our current consumption, we also want to minimize current leakage from floating I/O pins. We can use the app note AN2515 AVR Low Power Techniques, linked in the description below. Recall that we used this same app note in episode 6 of this series when performing low power measurements. But let's take a look at it again. There's a few relevant sections for us, including active peripherals, operating modes, choice of oscillator, and unused pins. So let's go through them now, starting with active peripherals. It mentions that in the register interface for each peripheral there is an enable bit, and that the peripheral operation can be affected by sleep modes. Next is operating modes, which tells us that there is 1 active mode and 3 sleep modes. Interrupts are used to wake the device from sleep, and the available interrupt sources depend on which sleep mode is in use. When an interrupt occurs, the device will wake and execute the ISR, or interrupt service routine, before continuing normal program execution from the first instruction after the sleep instruction. In active mode operation, the power consumption is proportional to the operating frequency of the system clock. However, it is noted that while the rule of thumb is that lower frequency correlates to lower power, sometimes the opposite is true. Basically, what this boils down to is that sometimes using a faster clock means the CPU will finish its task faster and then return to sleep sooner, which may result in a lower total power consumption. But at the end of the day, each application needs to be profiled in each of the operating modes and the duration in each mode to determine an appropriate power profile that meets the power requirements of the application. The available sleep modes are idle, standby, and power down. In idle sleep mode, the CPU stops, but no peripherals are disabled. Standby sleep mode allows the user to configure peripherals to be enabled or not by using the run standby bit for each peripheral in use. Wake-up sources relevant to this project are pin interrupts. Power down leaves only the watchdog timer and the PIT. The wake-up source relevant to this project again is the pin change interrupt. Since we want to put the host device to sleep and only need to wake when the button is pressed, which is a pin change interrupt, we can then use power down sleep mode. Now let's jump to section 7, choice of oscillator. Not only does the system clock affect the power consumption, additionally, the choice in oscillator affects the power consumption. For example, the trade-off between the external 32.768 kHz crystal oscillator and the internal 32.768 kHz ultra-low power or ULP oscillator is that the ULP oscillator consumes less current but is also less accurate. Because this project does not require high accuracy, the ULP oscillator is a better choice. It's important to note that this trade-off should be re-examined with each project's requirements in mind. It also tells us that disabling the clock source during sleep will lower the power consumption at a cost of increasing the oscillator startup time. We will be disabling the clock source during sleep to obtain improved power consumption, as oscillator startup time for this project is not a hard requirement. Now let's jump to section 9, unused pins. It tells us that all digital I/O pins are left floating by default to avoid hardware conflicts. A floating pin can cause sporadic internal switching and leakage current. We can minimize this by activating the internal pull-ups. Additionally, disabling the digital input buffer on unused pins further lowers the power consumption. Let's jump back to MPLABX, where we were looking at the port init function. In the port peripheral, we can write to the individual pins pin and control register. Alternatively, we can write the setting we want to the multi-pin pin config register. Let's quickly jump to the datasheet to section 18, port. And we want the register summary. Then click on pin config. It tells us for faster configuration of the port module, the multi-pin configuration write enables the configuration of several port pins in a single cycle. Writing to this register may be followed by a write to either of the multi-pin control, which is port X, pin control UPD, or set or clear registers to update the pin and control registers for port X. This register is mirrored across all port X modules. If we then look at the next register, multi-pin control update mask, if we write a 1 to a bit position in the bit field, it will copy the port X pin config register content to the corresponding port X pin and control register. If we write a 0, it will have no effect. Jumping back to MPLABX, we can see for ports A, C, D, and F that I have set the pin config register to disable the input sense configuration and enable the internal pull-ups. Then for ports A, C, and D, I have copied that across to all pins using hex FF. For port F, I have used hex BF, which will copy the settings to all port F pins except PF6, which is our button switch. Then for pin PF6, I have enabled the interrupt for rising edge and enabled the internal pull-up resistor. The button switch is active low, which means the interrupt will fire when the button is released on the rising edge. Finally, all port pins not in use have been tied high. Next, I've called the ADC Init function, where the configuration is as follows. Voltage reference, or VF, is VDD. Always on has been disabled. Run standby is disabled. Conversion mode is a single 12-bit conversion. Left adjust is disabled, meaning right adjust result. Free running mode is disabled. Initialization delay of 16 ADC clock cycles. No sample accumulation. ADC clock prescaler of 2. Sample delay set to 0. Sample length of 2 ADC clock cycles. Positive ADC channel A in 18, which is pin PF2. Negative ADC channel is ground. Window compare mode is inside window. Lower window threshold is 1000. Upper window threshold is 3000. If you're unsure of any of these settings, please see episodes 10, 11, and 12 in this series for more detail. Next, we call the USART Init function, which is configured for asynchronous mode, no parity, 1 stop bit, 8 data bits, and a baud rate of 1200. Now you might be wondering why I selected a baud rate so low. Let's jump to the datasheet section 27, USART, then click on the functional description, operation, clock generation, then finally the fractional baud rate generator. Under that is table 27-1, equations for calculating baud rate register setting. We are operating in asynchronous mode, and our main clock will be 32.768 kilohertz. Then under the table, it states that if we use asynchronous mode, S equals 16. If we plug those values into the equation, we get a maximum frequency of 2048 Hz. The most commonly used baud rate below that is 1200. For more information on setting up the USART peripheral, refer to episode 8 in this series. Next, we call the sleep init function, and we select the power down mode group configuration and also use the sleep enable bit mask. For more information on using the sleep controller, refer to episode 7 in this series. Next, we enable global interrupts with the SEI function. Now that the initialization has been completed, we will move to the next state, which is sleep. In the sleep state, we call the assembler command sleep to put the device into the sleep mode we set up in the sleep init function. Since we will be waking from a button press, let's jump to the ports.c file. First thing to notice is at the top of the file we have a volatile, unsigned 8-bit integer called button pressed. Next, I will scroll down to the interrupt service routine, or ISR, for the port F port interrupt vector. We have an if statement that checks if the source of the interrupt is pin PF6. If it is, we set the volatile variable button pressed to 1. I also have some other functions under the ISR. The first is called getButtonPressedStatus, which takes no parameters and has an unsigned 8-bit integer return. It simply returns the value of the variable button pressed. Then the next function is clearButtonPressedStatus, which takes no parameters and has a void return. It simply resets the volatile button pressed variable to 0. You may notice that there is not a set button press status, and that the variable is set directly in the ISR. This was intentionally done to avoid function calls in the ISR. Now returning to the main.c file in the sleep case. So after the assembler directive for sleep, we have an if statement that calls the getButtonPressedStatus function, and if that resolves to 1, then it calls the clearButtonPressedStatus function to clear the volatile button press variable, and then it sets the state machine to read ADC. If you're new to putting a CPU to sleep and waking on interrupts, upon waking the CPU, we'll first execute the code in the ISR, and then continue normal program execution from the first instruction after the sleep instruction. For more information on this, check out episode 5 in this series. In this case, the first instruction after the sleep instruction is an if statement determining whether the button pressed interrupt caused the CPU to wake from sleep, and if so, moving to the next state. Now the state machine moves to the read ADC state. Before we go through that state's implementation, let's take a look at the adc.c file. First, there is a volatile unsigned 8-bit integer variable called windowSatisfied, and a comment that this variable is set in the ADC window comparison interrupt. Next are two variables for bit shift and enob, which is effective number of bits. In this project, these variables are not used, but they were used in episodes 10, 11, and 12 in this series for increasing the effective number of bits from the ADC from 12 bits to 14 bits. The first function is ADC Init, which takes 17 parameters and has a void return. This function is exactly the same as the one used in episodes 10, 11, and 12 in this series. If you want more information, please revisit those episodes. Just as in episodes 10, 11, and 12, we have functions for ADC Enable, ADC Disable, ADC Start Conversion, ADC Is Conversion Done, ADC Is Windows Satisfied, ADC Start Over Sample Conversion, ADC Get Result, and finally ADC Get Oversampled Result. There are a few new additions right at the bottom. First, we have ADC Enable Power Rails Before Conversion, which sets pin PC3 high and pin PC2 low. Secondly, we have ADC disable power rails after conversion, which uses the pin N control register to both disable the input and enable the pull-up resistor for pins PC2 and PC3. Finally, we have the ISR for the window comparison, which uses the ADC0 window compare vector. Inside the ISR, it sets the volatile window satisfied variable and clears the interrupt flag. Let's return to main.c. In the read ADC state, we first call the ADC enable power rails before conversion function, then ADC enable. Note there is a 1 millisecond delay after these two function calls. This is so that the voltage reference, or VREF, of the ADC can stabilize before we take a measurement. We can find this information in the datasheet, section 38.12 VREF. In table 38-18, it shows the VREF startup time depends on the clock source used. If main clock control A in the clock control peripheral is 0 or 3, where 0 is the high frequency internal oscillator and 3 is the external clock or oscillator, then the startup time is 10 microseconds. However, if the main clock control A in the clock control peripheral is 1 or 2, where 1 is the 32.768 kHz internal oscillator and 2 is the external 32.768 kHz oscillator, then the startup time is 200 microseconds. I used a delay of 1 millisecond, which gives us plenty of extra time to allow the voltage reference to settle before the ADC samples the signal. Once the power rails have been enabled, and the ADC has been enabled, and the VREF has stabilized, we start an ADC conversion and wait for it to complete. Before we start writing to the data array, I want to clear the contents to be sure there's no old data present before we write the new data. Next, we have an if statement that checks the return of the ADC is window satisfied function. There's a comment above that explains when the ADC result is read, it clears the window comparison flag. This is why the window comparison must be done before reading the ADC result. The window comparison result is placed in the most significant bit of the high byte. Then the ADC result is read. Then we take the lower 8 bits of the ADC result and write that to the low byte of the data array. Next, we bitwise OR the high byte of the data array containing the window comparison result with the upper byte of the ADC result. Then we call the ADC disable function and the ADC disable power rails after conversion function to reduce the power consumption when the ADC is no longer in use. Finally, we change the state to switch to high-speed clock. In the switch to high-speed clock state, we will be using a 4 MHz main clock when we do the SPI data send. So we will call the main clock control function, and we will use the OSC-HF high-frequency internal oscillator. We will select 4 MHz as our clock speed. We will enter 0 to disable the prescaler, which will ignore any prescaler value we put in. And finally, we will disable clockout as it uses the same pin as the SPI client select pin PA7. We then have a while loop where we wait for the OSC-HF oscillator to stabilize. If you're unsure about this function or setting up clocks, please see episode 5 in this series. Then we will change state to send SPI. Now in the send SPI state, we will call the SPI Host Init function. Let's control-click to follow it to its definition in the SPI.c file. This is very similar to the SPI Host Init function that we created in episode 13 of this series. If you are unsure, please revisit that episode for more detail. The first thing we do is use the port mux peripheral to set the pins to be used, and they are PA4, PA5, PA6, and PA7, which is the default. Next, in the Control A register, we set the data order to send the most significant bit first and to disable the clock double. Next, in the Control A register, we enable our device as the host or master, and we set the prescaler to divide by 16. Since we have a 4 MHz main clock, this will give an SPI clock of 250 kHz. Now in episode 13, we used a 1 MHz SPI clock, so you might be wondering why we didn't use the same clock speed in this project. I found running an SPI clock of 1 MHz with a main clock running at 4 MHz when connected to the client device did not allow enough time for the client device's CPU to process the interrupt and to do something with the data before the second byte arrived. To fix this, I could have used a faster main clock for the client device, but that will consume significantly more power, and low power is a focus point of not just this project, but the entire video series. As a result, the better option was to use a slower SPI clock from the host device to give the client device time to process the interrupt and do something with the data before the second byte arrived. Continuing on, we will use SPI mode 0 just as we did in episode 13. Then we need to set the MOSI, SCK, and SS pins as output, and the MISO pin as an input. Next, since the SS pin to the client device is pulled low before sending data, I will start the SS pin in a high state. I need to enable the TX complete interrupt, and finally enable the SPI peripheral. Returning to the main.c file, then I call the SPI select client function, which pulls the client select line low. I will then use our spin lock function to create a delay of 4 milliseconds before sending SPI data. This is to give the client device time to wake from sleep, process the interrupt, and process the first byte before the second byte arrives. Next, we call the SPI 0 Write Block function. Let's control-click to see its definition in the SPI0.c file. The function takes two parameters, a pointer to the data array, and the size of the block being sent. Inside the function, we create two new variables called receiveData and a pointer called blockPointer. The next thing to do is make a copy of the pointer so that we don't modify the pointer being passed to the function. Next, we have a while loop in which we post-decrement the size parameter. Inside the while loop, we write the data byte to the SPI data register. Then we have a while loop that waits for the receive complete interrupt flag to be set, and this is for the data the client will be sending back. We then write the received data into the SPI data register, and then we increment the block pointer ready for the next byte. Returning to the main.c file, after the SPI 0 write block has been executed, we then deselect the client device, disable the SPI peripheral, and disable the pins by setting the pin and control register to disable the inputs and activate the internal pull-ups. Finally, we set the state to switch to low power clock. Now in the switch to low power clock state, we can then call low power clock control, where we use the internal 32 kHz oscillator. We do not use a prescaler, which ignores whatever we write to the prescaler setting. Run standby is disabled, and clock out is also disabled. We will then wait until the OSC32 oscillator has stabilized. Next, we have a function turn off unused pins before sleep, which disables all pins on port A which have been used for SPI. Finally, we set the state to sleep. And that's it. It's a pretty straightforward state machine implementation. In the next video, we will go over the client device implementation and test everything, including the power consumption of both devices, and then also go over some gotchas encountered while building the final project. Stay tuned!